It's about time. So welcome to the Combinatorics seminar, everyone. Today we're happy to have Farid Aliniaeifard, hopefully I got it right, from University of British Columbia. And he's going to talk about a categorification of the Malvenuto Reutenauer
Yes.
algebra by a power of groups. And this is a pre-seminar, so feel free to ask any questions that you have. The main seminar will start at 4:10. Take it over.
Yeah. First of all, thank you very much, Sarah and Lei, for giving the opportunity to talk here. Uh, and it this slide has many difficult names: categorification, Malvenuto, Reutenauer, and me. But Malvenuto and Reutenauer are quite famous, but I'm not. So, right. So this work is joined with Nat Thiem from University of Colorado Boulder. And here I want to talk about the categorification of the Malvenuto Reutenauer Hopf algebra, actually. So in this pre-seminar, I will try to give a sense of what is categorification in general. When we say we want to categorify a Hopf algebra, what does that mean? And I will try to do this one by categorification of the Hopf algebra of symmetric functions. So actually here, we don't talk about Malvenuto Reutenauer. Later in the main talk, we will talk about Malvenuto Reutenauer Hopf algebra. Okay, so first, we should know what is a character. A character is a composition of a homomorphism and a trace of some matrices. So a homomorphism is a group a representation is a group homomorphism from a group to the general linear groups. This is the set of all invertible n by n invertible matrices. And a character is actually the trace of that representation. So if I have my representation from G to GLN, then I look at the trace of XG, the image of G on representation, and I look at the sum of the elements on the main diagonal. So this will give me the trace, and this will called character of that representation. So let's do an example to make it more clear. So here we have a symmetric group of order 3, which is the set of all functions from 1 to 3 to 1 to 3. And in here, I use one line notation of permutations. So here, if I have 2, 1, 3, that means 1 goes to 2, 2 goes to 1, and 3 goes to 3. If I map, for example, 1 to 3 to a matrix such that I look at the first column, here is 1, so I put 1. I look at the second column, here is 2, so I put 1 here in the second row. And here I put 1 in the third row. I go to the next permutation, which is 2, 1, 3. I look at the first column, and in row number 2, I put a 1. I go to the next. At row 1, I put 1. And in the end, at row 3, because here is 3, I put 1. If we continue this one, and we find in this way the image of all permutations of order 3, then we have a representation of S3. And when we look at the characters of this permutation, it's like this. So the chi of 1, 2, 3, which is the character of that representation I just introduced, is equal to the trace of this matrix, x of 1, 2, 3. So I look at x of 1, 2, 3, and I look at the sum of all elements on the main diagonal, which is here is 3. And if I go to the next one, I look at the trace of x of 2, 1, 3, which is 0 plus 0 plus 1, it's equal to 1. So if I continue this one, I will find the character of this representation. Okay. So I have two main characters here that I highly use them in the seminar talk. The first one is the trivial character. I pick up an element and I map it to trivial element, which is 1 for complex number. So every group element goes to 1. This is giving me a character that we call it trivial character. And regular character, it's a function from G to complex number that maps every element of G to 0 except the identity, and it maps the identity to the cardinality of the group. So these two characters are quite important for me later. And then when we look at the set of all characters, there is a very important function between character which is called inner product. And what is inner product of two characters? If I pick up chi and psi, the characters of G, then the inner product of them is actually, if I put chi G and psi G conjugate in a set and I do the average of them. So the average of those elements will give me the inner product of these two characters. Previously, I had this character that we just computed it. So if I want to compute the inner product of chi by itself, I have 1/6, the cardinality of group, because here this is a character of S3 and the cardinality of S3 is 6. So then chi of 1 to 3, I should go with all elements. Chi of 1 to 3 times chi of 1 to 3 conjugate, then chi of 2, 1, 3, chi of 2, 1, 3 conjugate until the end, all of the elements in S3. So we will see that chi of 1 to 3 is 3 and its conjugate is 3. So I put 9 here. Then I go to the next one, which is 1 times 1, and I go to the end. So it's 1/6, and this sum is 12, so this is 2. And if I do the inner product of the trivial character by itself, everything is going to 1. So I have 6 here, and then the cardinality of group is 6. It's equal to 1/6 times 6, which is 1. These characters that their inner product to themselves is 1 are very important. Actually, they are giving me the building block of character theory. So, and what is that one? A character chi is called irreducible if its inner product to itself is equal to 1. Why these are important? Let's go to class function and see. So a function that is constant over all conjugacy classes is called a class function. So therefore, if I pick up f, I call f a class function. If I have two elements, G and H in G, then f of H inverse must be equal to f of G for any H and G inside G. Okay, and one important thing here is characters are class functions. So if I want to compute chi of H inverse, this is equal to the trace of some representation X of H inverse. So this is a group homomorphism. This X is a group homomorphism. So I can write the trace of XG, XH, XG, H inverse. And since trace of AB is equal to trace of BA for two matrix A and B, then this one is equal to trace of XH, XH inverse and XG. This is going to identity. So the only thing that is remaining is trace of XG, which is chi of XG. So these two are equal. Therefore, for any two element in some in the same conjugacy class, every character is fixed on that one. Therefore, every character is a class function. And irreducible characters is giving me a basis for the set of all class functions. And moreover, every character is a positive linear combination of irreducible characters. So two things here are very important. First, every irreducible character is constant on conjugacy classes. And second, every character can be written as linear combination of uh, of irreducible characters. So if I construct a table that the columns are indexed by conjugacy classes and the rows are indexed by irreducible characters, and each entry, for example, 2 here, is the value of this character on some element of this conjugacy class, then this will decode everything about character theory. Because every character is a positive linear combination of irreducible characters, and irreducible characters are constant on conjugacy classes. This is called character table, and it's encode everything about character theory. Okay, and the kernel, so in the next talk, I will refer to kernel a lot. So kernel of a character is those elements in G that the value of the character at G is equal to the value of the character at 1. For example, if we look at here, the kernel of chi1 is 1, 1 is these 3 conjugacy classes. Why? Because the chi1 of 1 is equal to 1, and the chi1 of each element here is equal to 1. So these 3 elements are in the kernel of chi1. And the red ones are in the kernel of 1, and the kernel of each one is distinguished by a color. Okay, so sure.
I have a question. Are we assuming that G is finite?
G, the group?
Yes.
Yes, absolutely. All of the groups that I'm working with them here, they are finite. So all of my talk is about finite groups. Yes, thank you for asking. Yeah, perfect. So here I have 2 characters that their kernel is the same, which is trivial. What if I put them in one block, and based on this one and these 2 elements that they are only in the kernel of 1, I make my character table divided to some blocks? What will happen? And if you look at this block, the sum is 0. So the sum of the columns in that block is 0. I can do this one also in a bigger way. If I put this one as a block, and so I divide my character table to 4 blocks, if you look at this one, the sum of this is -1, the sum of this is -1, the sum of this one and this one also is -1. So actually, the sum of every column here is -1. So later in the main talk, I will construct something out of these features of character table, and I explain why this is happening. Okay, the kernel, so when I have character table, actually I can say anything, everything actually about normal subgroup, because the kernel of each irreducible character is a normal subgroup, and each normal subgroup is intersection of some of kernel of some irreducible characters. Okay. So some useful functions. The first one that I want to talk about it is induction. Induction is a way that we lift, or by having a character of H, which is a subgroup of G, we construct a character of G, the bigger group. So if H is a subgroup of G, then the induction of a character of H is equal to this one. And what does that mean? So here the induction maps G to the sum of precise circle, which this one means whatever is outside H, this precise circle maps it to 0. So, and this sum is over all of these elements. And in the end, we divide it by cardinality of H. As an example, here, if I take this group, which is abelian group, and generated by their elements are 1A and B and AB, and I pick up a subgroup of it, which is 1 and A, then I pick up a character of this subgroup, which maps trivial element to 1 and A to -1. This is a character of H, and then I can induce this one to a character of G in the way that we explained. And here, if you look at all of these elements, since I have an abelian group, they all map to psi of A, which is -1. So I have 1/2 times 4 times -1, which is equal to -2. Okay, so now we want to talk about restriction. The restriction functor, or let me say function, it's exactly the same as restriction to some subset as we work with functions. So here, if I have H a subgroup of G and a character chi of G, then the restriction of the character over H is mapping G to chi of G. This is quite well defined and we should not be worried about anything. Again, as an example, if I pick up this chi, which is a character of G, which maps 1 to 1, A to -1, B to -1, and AB to 1, then the restriction of this character to H, since the elements of H are 1 and A, when I look at the restriction at 1, it's 1 because chi of 1 is 1, and the restriction of chi over A is -1 because chi of A is -1. Okay, then now I want to talk about integer partition because I want later talk about symmetric functions and also how they are isomorphic with class functions of symmetric groups. So integer partition, an integer partition is a tuple, is a non-decreasing tuple that the sum is equal to n. So here I have a partition of 4 because this tuple is non-decreasing and the sum of these 4 elements is 4. And this is the notation for integer partition. So we read 2, 1, 1 is a partition of 4. The conjugacy classes of Sn, permutation group, and also irreducible characters of Sn, both are indexed by integer partitions. So, and here we denote by IRR Sn, the irreducible characters of Sn. Then if I look at the class functions of Sn, actually the characters, the irreducible characters of Sn is a basis for it, and we index it by integer partitions. Now, if I look at the tower of symmetric groups, which Sn is a subset of Sn plus 1 in a way that we just map Sn to those elements in Sn plus 1 that maps n plus 1 to n plus 1. In this way, we have a tower of groups of symmetric functions, and then I look at the class function of each of these elements, and then I direct sum all of them, and then I have a new vector space. I have a graded vector space. So,
sorry, what do you mean by the class function? I thought like class function was a description of functions.
So class function is a function at the beginning from G to complex numbers. So if I have a class function is a function from G to complex numbers that is constant over conjugacy classes. So, but when we say the set of class functions, it's fixed, right? It's the set of all class functions of some groups.
So CF of Sn is the set of class functions on Sn.
Yes, exactly.
And when you say the direct sum of those sets, are you talking about their disjoint union or their Cartesian product, or?
I see. So here, I define the CF of Sn as a span of irreducible characters.
Oh.
Right? Yes. So sorry if I didn't get your.
Sorry, this went a bit fast. I missed that part. All right.
Oh, okay. No, that's my fault. Yeah. So then we add them up all together. We have a graded vector space. And now, if we go forward, I want to make this graded vector space a Hopf algebra in this talk, I probably do not talk about Hopf algebra in details, but in the next talk, I will give a definition of Hopf algebra over there. So first, I need to know what is the tensor product of two characters. If I pick up a character of G and a character of H, the tensor product of them, like here I have chi, a character of G, psi, a character of H, then it's act like this. When it acts on G and H, it's the product of chi of G and psi of H. Sorry for this typo. And this is always a character of G times H. And actually, if we want to look at all irreducible characters of G times H, is the tensor product of all irreducible characters of G and irreducible characters of H. Okay. And then by using induction, I define a product for the class functions in this way that if I pick up a character from Sm and a character from Sn, then I induce that one because this one gives me a character of Sm times Sn, and I induce it to Sm plus n. And this will give me a product for the set of all class functions of symmetric groups. And the coproduct is coming from restriction. So if I pick up chi, a character of some Sn, and then I restrict that chi to Si times Sj, when for all I plus j is equal to n, this is give me the coproduct for the set of class functions. And with this product and coproduct, that graded vector space is a Hopf algebra. So now we go to symmetric functions. A symmetric function is a formal power series that is the degree of monomial is bounded, and actually it's invariant under the action of all symmetric groups together. So what does that mean? If I have a function f and I act by a permutation sigma on it, in f I replace x of 1 by x of sigma 1, x of 2 by x of sigma 2, and so on. This one must be equal to f. Then we call this one a symmetric function, and I use sim for the set of all symmetric functions. So the symmetric functions has a very nice basis that they call it sure functions. And the sure function, here I do it by, I define it by example. For example, if I pick up the partition 2, 1, I put two box here and one box here, one box over there, and I should fill out these boxes with two rules. First, the rows must not be decreasing, and also the columns must be strictly increasing. So here I can have 1, 1, and then 2. I can have 1, 2, 3, 1, 3, 2. And each of these are correspond to a monomial. For example, I can have x1 squared x2, x1, x2, x3, and x1, x3, x2. So when I add up all of these monomials that comes from filling of those tableau, then that will give me sure functions. Sure functions are giving me a basis for symmetric functions in a way that the degree n symmetric functions are spanned by sure functions indexed by integer partitions. And I add them all and make it give me the symmetric functions. Now if I map sure function to the character, to the irreducible character, then I have a Hopf isomorphism. So this will give me a Hopf isomorphism. And when we look at combinatorial Hopf algebras, we have a very nice graph that shows the relation between different some combinatorial Hopf algebras, for example, non-commutative symmetric functions, quasi-symmetric functions, and free quasi-symmetric functions. This is Malvenuto Reutenauer Hopf algebra. So the question is, we did this one for symmetric functions. We find an isomorphism from symmetric functions to class function of some tower of groups, and these two are isomorphic. Can I find some tower of groups in a way that if I make a Hopf algebra of that tower of groups, can I find something that is isomorphic to NSIM, or isomorphic to quasi-symmetric functions, or isomorphic to Malvenuto Reutenauer Hopf algebra? And this is the question that I will answer in the next talk. And I show that actually for Malvenuto Reutenauer Hopf algebra, we can do this. We can find a tower of groups and construct a Hopf algebra of super class function of it in a way that one is isomorphic to Malvenuto Reutenauer Hopf algebra. However, still it's not known that how we can translate these functions, these decent functions from Malvenuto to quasi-symmetric functions as a functor. Still, we don't know that one. And I will talk more in details about this diagram in the next talk. So thank you very much. And if there is any question, please.
Well, shall we first thank the speaker together?
Thank you very much.
Okay. Any questions?
I do have a quick question for you. So so was something that you just described the concept of categorification? Because I've only heard that word and have no idea what it means.
Great. Yeah, that is a great question. And actually, right after this one, I should explain that, which is coming from next talk. But let me explain. Actually, that's my goal, to say what is a categorification here. So what is categorification? So I pick up symmetric functions and I pick up some class functions and I show these two are isomorphic as Hopf algebras. But what is categorification? Categorification is I pick up a Hopf algebra and I pick up a category in a way that I find the basis for my Hopf algebra and map it to the simple objects in my category in a way that the product and coproduct map to my two of the functors of that category. So here, for example, for symmetric functions, I have symmetric functions, my Hopf algebra. I have the category of all representation of symmetry groups because characters and representations are the same, right? Then here I have a basis, which is sure functions. And here I have irreducible representations, which are simple objects in my category of representations, and induction and restriction in my category of representation are equivalent with the product and coproduct of symmetric functions. So categorification means translating everything from set to categories.
Gotcha. Okay, that makes perfect sense. Thank you.
Yeah, thank you.
Well, feel free to repeat it again in the next talk too, because everybody who comes to the pre-seminar wants to hear things twice.
Yeah, absolutely. Actually, this is the extended version of the first 5 minutes of my talk. Yeah, thank you.
Any other questions? Okay, shall we thank the speaker again and enter the 10-minute break?
Thank you. Let me